Okay. Good morning. Today, in the in the tutorial session, I will run an example with condition variables. So the reason I'm doing this is because in 252 the focus has been, I mean, as far as I know, according to the feedback I got from the students, in 252. You basically learn to use semaphores and do a lot of practice on semaphores. And condition variables are just mentioned, and probably one or two examples you see. So here I give you an example of using condition variables for a problem that you probably have seen in ECE 252. And then through quizzes, we practice more on condition variables. So I think at least 2 or 3 quizzes are on condition variables. And so basically you will see a reoccurring example over 2 or 3 quizzes. So okay, with that, let's just go over condition variables, what they are, and then I'll start talking about readers, writers example. So condition variables are an alternative to semaphores. To actually condition to, let me go one slide before this. So semaphores are just complicated and they're double used. One usage is basically for using them as mutexes, and the other one is to use them for waiting and signaling, and that makes them complex. And as you probably remember from ECE 252, the order that you call P has implications. It might, if you don't follow the order, the proper order, you might actually get deadlock. So overall, a code written using semaphores is not that pleasant to analyze and understand. An alternative to that is to use monitors, and a monitor is basically a single mutex with one or more condition variables. The mutex will be used for mutual exclusion, and conditional variables will be used for the signals and the weights. Now, there are 3 main functions for a condition variable. There's a weight, there's a signal, and there's a broadcast. With weight, we pass the mutex, and what happens in the weight is the thread goes to sleep, and atomically the mutex is released or unlocked so that other threads can enter this critical section and potentially send a signal. When a signal is received, the thread that receives the signal, so when a signal is sent, if there is at least one waiting thread, that waiting thread gets signaled and wakes up. When we say it wakes up, we're not talking about running. We're just saying that it goes to ready list. So the scheduler can schedule that thread. Maybe not immediately, but at some point. When broadcast is sent, all the waiting threads will will be moved to the ready list. So from waiting, they become all ready. And again, we're not talking about running. So you just become ready, and then you will have to run later whenever the scheduler decides to schedule you. A very important property of condition variables is that they are memoryless. So they do not remember the previous calls to signal and broadcast. What do I mean by that? So they don't have any, in semaphores, you had an integer, a non-negative integer that would increment or decrement according to P and V's. So if you had, let's say 5 V's or 5 signals on a semaphore that was initialized to 0, then you would know that the value of your semaphore is now 5. So now 5 P's or 5 weights will go without waiting. So we kind of memorized how many times V was called so that that many P's could go without waiting. In condition variables, if you call signal 10 times, all 10, if there is no waiting thread, all of those signals will be forgotten. We're not going to memorize how many times signal was called. So let's say you call signal 10 times, and then another thread comes and calls wait. The waiting thread is going to wait. It's not going to say, okay, because there was 10 calls to signal before, so I'm now going to go without waiting. No, it's memoryless. We'll forget about all those signals. And this is one of the most important differences between condition variables and semaphores. The rule is to always hold the lock when you want to send a signal or you want to broadcast. And obviously, if you want to call wait. By holding the lock, I mean locking the mutex. Now, this wait function, I get students asking me questions about it. So it's kind of like a it's kind of like a special function. When you call wait, inside wait, you're going to be unlocking the mutex and go to sleep atomically, meaning that at the same time, both of these two happens. The lock is released and you go to sleep, and without interruption, right? So both of these two happen. Now, when you receive a signal, your task or your thread is going to become ready. Now, at some point, this task will be scheduled and starts running. Where does it wake up? It wakes up inside wait function. Now, inside wait function, before it returns, it has to lock the mutex again. It has to lock the mutex again. So if I write it for you, so inside wait, which requires a mutex star m. So we will see how we can implement wait, but I'm not going to touch on that yet. That we'll talk about in the lectures. But somewhere here, atomically, we're going to do m.unlock, go to sleep. Basically suspend this thread. Now, when you wake up, you're going to wake up at the next line from this. So you will wake up. The first thing you do is m.lock. And I'm looking at the internal of this wait function. Now, when you call m.lock, are you guaranteed that you can lock the mutex? Not necessarily. Maybe the lock is maybe the mutex is locked by someone else, right? You got a signal, right? So you are moved to ready, but you're still not guaranteed to run yet. Now let's say some other thread comes and they get scheduled before you, right? They also become ready and they get scheduled before you. And then maybe they lock the mutex. And maybe they get suspended. Like let's say the timer goes off and they get suspended, and the operating system context switches to you. So now you wake up. The first thing you do, you call this m.lock, but mutex is already locked by someone else. So what happens to you again? You're going to go to sleep again, meaning you're going to be put on the waiting list of the lock this time, right? So now you're going to be waiting for this lock to be unlocked so that you can lock it again. And at some point, whoever holds the mutex, whoever has locked the mutex, is going to unlock the mutex. And eventually, you're going to be the one who has the lock. So then again, you wake up after this line. And at that point, you do have the lock, so you can return from wait. So when we get out of wait, we enter the wait with m.lock, meaning that the mutex was locked. We get out of it again with m.lock, meaning that when we went into the wait, we had the mutex locked. When we get out of wait, we again have the mutex locked. So that's what wait does. But then inside wait, you could go to sleep multiple times, right? The first going to sleep is because you wanted to wait. The second going to sleep and again, the second one might be because you want to lock a mutex that is already locked and you get suspended until you eventually lock that mutex. So that's the internal of wait. I got a question. So wait wakes up one thread while broadcast wakes all threads. Yes. So wait wakes up a single thread if there are any. If there are none, then signal gets wasted. Nothing happens. If there are no waiting threads, signal gets wasted. And broadcast wakes up all threads if there are any. And if there are none, again, it gets wasted. And by waking up, all we mean is to make their state ready, not to run them. They will eventually run, but whenever the scheduler wants them to. Okay. Okay, and this is like a design pattern, the coding for using monitors. So in the thread that is going to wait, like before, so we lock the mutex and unlock the mutex at the beginning and end of our function. So this is a theme now. You should notice. So at the beginning of our function, at the end of our function, we ensure mutual exclusion. Now, in the middle, where we want to wait on the event, we put the wait in the while. So I think, if I'm not mistaken, you might have been told that this needs to be if, meaning that you just check the condition, and if that condition is true, then you call wait. But as you will see, this has to be while. It should not be if. You have to keep checking that condition, and the reason is precisely what I just said before, which is that when you get a signal, it doesn't mean that you're gonna run. it just means that you have become ready, right? So when you run, maybe somebody, let's say like the example of producer consumer. Let's say you wanted to consume an item from a bounded buffer and there was no item, so you wanted to go to sleep. So you call wait. Now, at some point, a producer comes and produces an item and then sends a signal to you that you are sleeping. So you receive a signal. Now you become ready. Now, right before you run, another consumer comes and they get scheduled first, right? So now there are two consumers. One is you, who woke up from by a signal, and a new consumer that just came. And let's say the operating system scheduler picks the new consumer, not you, right? For whatever reason. So now the consumer runs and the consumer consumes the item and exits. And now the operating system schedules you. Now there is no item, so you should go to sleep again. That's why you should check this condition in a while. You cannot check the condition just once. Yeah, so somebody is asking what is test shared state. So this is the condition that you want to wait for. For example, in the producer consumer, you want to check if the queue is empty, right? And this queue is a shared state between all the producers and all the consumers. So you want to check the state of it. You want to say, for example, if queue is not empty, then consume. But if it is empty, then you want to wait. And what I was just saying is that you shouldn't say if queue.empty wait. You should say while queue.empty wait, right? Okay, so this is probably the main difference from what you learned from 252, that we use while, not if. And in the thread, for example, this could be the producer, and this could be the consumer. So then producer, when they produce an item, then they send a signal to the condition variable that consumers are waiting for or on. Okay, so with that, let's go and look at an example using condition variables. Okay, so let's look at these guys. Didn't download. Download. Oh, it's not downloading it. Go to GitHub, tutorial, and reader writer. Okay. So here's the problem that we want to solve. You probably have seen it in 252, and you probably have implemented it with semaphores. I don't know. I'm just guessing. You guys tell me in the Q&A if that's true. So the motivation is we have this shared database and we have two classes of users. We have writers and we have readers. Now, the conditions that we want is that the readers are not going to modify the database. They're going to just read the database. The writers, however, are going to both they could read or write to the database, read from and write to the database. The database can support multiple readers at the same time, so it's fine if a bunch of readers want to read the database at the same time. That's fine, because they're not going to modify it, so they can just read it. So that's fine. But at any given time, we only want a single writer to have access to the database. So if there is a single writer in having access to the database, we don't want any other writer or any other reader to have access to the database. But if there are a bunch of readers having access to the database, that's fine. So we want to design a specific lock for this. So we want to name our lock reader-writer lock, and then have functions specifically for this. So if you are a reader, you can acquire this lock as a reader. If you are a writer, you can acquire this lock as the writer. And this is kind of like the summary of what we said. So if you have two threads, both of them are writers, we don't want them to have access. If thread 1 is a writer and thread 2 is a reader, this is also a no. If thread 1 is a reader, thread 2 is a writer, it's a no. But if both threads are readers, it's okay for them to access the data at the same time. Okay, so we're gonna design this a specific lock. We're gonna call it reader-writer lock. Now, for our design, we'll use a single mutex. This mutex, we're gonna use it whenever we want to change the state of the lock. So this is not a mutex that readers or writers are going to use. This is a mutex that we will use to change the internal state of the lock. So for those of you who remember the lecture yesterday, we had the similar situation. We used the spin lock whenever we wanted to modify the state of the mutex. So now we're designing this reader-writer lock, and it has internal state. So whenever we want to modify the internal state of the lock, we'll use this mutex for mutual exclusion. On top of that, we're going to have two condition variables, OK to read and OK to write. So when it is not OK to read, then the readers will wait on OK to read. And when it's not OK to write, the writers will wait on OK to write. So that's that. Now, we also have 4 variables to track how many active writers, active readers, waiting writers, and waiting readers we have. So 4 variables for that. And then we want this class to have 4 functions: acquire the lock as a reader, and then release the lock as a reader, acquire the lock as the writer, and and release the lock as a writer, right? So once we design this class, then our threads, depending on their role, can use this special lock to access the database. If they want to read, they acquire it as a reader. If they want to write, they acquire it as a writer. Okay, now let's look at read. So this is a design pattern, as I said. So if you are a reader, you acquire the lock as a reader. If you are a writer, you acquire the lock as a writer. So this is our end goal, what we want the threads to the programmers to use this lock for. This is how it's going to work. Okay, now let's give it a shot. Let's try to implement this. So I will start with acquiring this as a reader. Now, at the beginning of our function, what should we do? We should lock the mutex. We want to change the internal state of our lock. So we use the mutex to make sure that this happens with mutual exclusion. Now we're going to check and see if there are any active writers or waiting writers. So if there are active writers or there are waiting writers, we're going to wait. And note that I'm using while. I'm not using if, because I'm going to wait now, right? So if there are this condition holds, then we say, OK, now I'm going to go and wait. And I am a reader, so I'm a waiting reader. So we increase waiting reader. We do ++, and we wait on the condition variables that we have. OK to read that wait. When we wake up from wait, and if we wake up from wait, it means that somebody has sent us a signal. So when you wake up, you're no longer a waiting reader. So you decrement the WR by 1, and then you go up and check again, right? So this whole thing has to be in a while. And if you get out of this while, it means that you are now an active reader. So it means that you didn't need to wait, which means that the conditions were all good. So you can actually start reading. So you become active reader. So AR++, and then you release the lock. You unlock the mutex. So you should, the fact that I'm here unlocking the mutex should not make you wonder about the programmer who is going to use this reader-writer lock, because this mutex, the programmer is not going to know about it, right? The programmer is going to use this acquire RL to acquire this reader-writer lock, not to lock this mutex, right? This mutex, we're using it for ourselves to change the state of the lock. And it has nothing to do with the end user using this reader-writer lock, right? It's going to be the end programmer is oblivious about this mutex. This is an internal state. OK, so somebody's asking, did you lock the mutex in wait a second time? The second time. So wait, we're just using it. Internally, wait will release the mutex when it goes to sleep, and it locks the mutex when it wakes up. So we shouldn't care about that now. We'll care about it when we want to implement it. So on Tuesday, when I talk about implementing condition variables, I tell you how we can implement wait. But at this point, I'm just using wait as a function. So I don't care about how wait is implemented. But internally, I know that the wait function has, when it suspended me, it released the mutex. And when I woke up, and now that I'm running, I do have the mutex locked. OK. Now continue with, so again, this is the most important thing. This mutex is used to change the internal state of the reader-writer lock. OK, now let's look at the release. If we want to release this lock, what are we going to do? Again, we're going to lock the mutex. Now we're not going to be an active reader anymore because we want to release the lock. So active reader minus. Now we're going to check and see if anybody is waiting. So if there are active readers in the system, then we don't do anything. So we're done with reading, but maybe some other people are still reading. In that case, we don't do anything. If active reader is 0, it means that there is nobody else reading, so I'm the last one. And if there are waiting writers, so while we were reading, maybe some writers came and got to be suspended. So if there are waiting writers and no active reader, then we send a signal to them. So we say, OK to write, signal. So there are writers waiting. So we tell them that, OK, now it's safe for you to wake up because there is no active reader anymore. Otherwise, we don't do anything. So if there are no waiting writers, or if there are other active readers, then we just decrement active readers and exit, nothing else. OK, so we kind of implemented these two. Let's now implement acquiring the writer lock and releasing it. So again, lock the mutex. If you want to acquire the lock as a writer, you have to check if there are active readers or if there are active writers. In both these two conditions, you have to wait. So that's what's going to happen. You're going to wait. Very similarly, if you wake up, you decrement. When you go to sleep, you increment. And eventually, when you get out of this while, you are, in fact, an active writer, so active writer plus plus. And when you want to release your lock as a writer, what should you check? You have to check to see if there are other waiting writers, because when you were writing, there might have been other writers that wanted the lock and they got blocked. So you're gonna just go and wake them up. So if waiting writer is more than 0, you send them a signal. Otherwise, if there are no waiting writers, then you might want to go and look at waiting readers. So now, if there are no waiting writers, but there are some waiting readers, then you can broadcast. So this is where I broadcast, because all of them now can go and read, not just one of them. I can tell them all to go and read. And finally, I release the mutex, unlock the mutex, and I exit. OK, so that's the implementation. Now, I put the code, so I kind of like merged the code. So this is the code for acquiring the reader lock. So oops. So this is to acquire the lock, and this is to release it. This is to acquire the lock as a writer, and this is to release it. So I just put all our implementation in these functions, and then here is where you are gonna read and write, and here is where you're gonna just read. So now let's run this example, right? So somebody's asking, don't we need an else block in release writer? Don't we need an else? No, these are the two only conditions that we have to care about. So either there are waiting writers or there are waiting readers. In these two cases, we signal. If there are none, then we just exit. We don't signal. What's the point? There is nobody waiting. Who do you want to signal? So there is no other else. So it's an if there are waiting readers or waiting writers. In these two cases, we broadcast or signal. Otherwise, we don't do anything. OK. Now let's run an example with this. So let's assume that initially there is all these variables are 0. So I'm looking at the internal state of my lock. There is no active or waiting reader, and no active or waiting writer. So all of them are 0. Now let's say the reader 1 comes in. So reader 1 comes. So it wants to read. What does it do? It gets the mutex. It checks these. It doesn't hold. So it moves from the while. It becomes active reader. It unlocks the mutex and it goes to read. Now let's say at this point R2 comes. Now R2 also acquires the mutex, locks it. And note that it can do it because reader 1 released the mutex because it was done with the internal. So this is the internal state. Of the lock. And we're using this mutex every time we want to access these variables. So then this reader also checks this, and there is no active writer or waiting writer, so it also jumps. It becomes second active reader. So now AR equals 2. So we have increased AR to 2. And this guy also goes and reads. Let's say at this point a writer comes, right? Now what happens to this writer? It's going to lock the mutex. It's going to check. Now it checks for active writers and active readers. Now we have 2 active readers. So it's going to wait. So then it increases the waiting writers to 1, and it goes and waits. So it goes to this wait and it gets suspended. It doesn't get out of it. So at this point, it gets suspended. It releases the mutex so that others can use this mutex. If it goes to sleep without releasing this mutex, then nobody else can then change the internal state of the lock, and we will be stuck. So that's not going to happen. Now let's say R3 comes. What happens to R3? Now R3 is going to check active writers and waiting writers. Now, because there is a waiting writer has become 1. So now this reader is not allowed to go in because there is another writer who wants to go. Then this guy is going to go and wait. It gets suspended. So R3 gets suspended. Now at this point, we will have a waiting reader, a waiting writer, and 2 active readers. Now, let's say that R2 wants to release the lock. So R2 says, I'm no longer active reader. So active reader becomes 1. It checks there is another active reader, so it doesn't do anything. Now, let's say R1 wants to get out. R1 also decreases active reader. Now active reader is 0. Now there is no other active reader, but there is a waiting writer. So we send a signal to the writer. So at this point, we send a signal. This means that that writer 1 state changes from waiting to ready. It doesn't mean that we're gonna run it. It just means that we're gonna put W1, the writer 1, on our ready list. That's all that's gonna happen. And we will continue with this R1. So R1 then releases the mutex. Now, operating system probably chooses, there are no other threads that are ready, but the writer. So now the writer that got the signal wakes up from within the wait, and let's say it successfully can lock the mutex and get out. So it wakes up inside wait, tries to lock the mutex. At this point, it's successful because nobody else holds the mutex. So it locks the mutex and gets out and decrements the waiting writer. It has to go up and check again. So it goes and checks again, and there is no active writer or active reader. So it becomes an active writer. So active writer plus plus. Now we have 1 active writer. it releases the mutex and it starts reading and writing. Now let's say at some point it wants to now get out. So it's no longer active writer. It looks at other waiting writers. There are none. It's 0. It checks for waiting readers. There is one waiting readers. This is R3. So at this point, it broadcasts to all of them. So there is only one of them. So at this point, R3 becomes ready. It unlocks the mutex. Then we go to R3. It wakes up from within the wait. It locks the mutex and so on and so forth. Okay, now let's analyze our solution. We have a solution we have implemented. Now, in our implementation, we're doing some stuff that we want to analyze and see what the implications of those are. The first one is a reader checks for active reader or waiting writer, and then sends a signal. What if we get rid of this and always send a signal to writers? So instead of checking if there are active readers or waiting writers, we just always send a signal to writers. Is that going to make our implementation incorrect? Okay, somebody's asking, what's the point of having mutex unlock and mutex lock at the middle? Right, so this is kind of, it's not in the middle. So this function is the acquire RL. I just put the code of acquire RL there, right? And then this is the release RL. These are the two functions that we implemented. So I just put their code here. And the point of releasing this mutex here is because we're done touching or modifying or reading the internal state. So here, when we're reading our database. We're not reading these variables, right? So this read is to the database. This is like, you know, this is for your ATM or for your website or whatever database you have. You read your data. Now, this mutex, you use it to read the internal state of your lock. So once you're done with that, you can release that mutex. Okay. Now, okay, question. Can I get rid of this line and always send a signal to writers? Would that change the correctness of my implementation? The answer is it's not going to make it incorrect, right? So you can indeed send signal without checking if there are waiting writers, because if there are no waiting writers, your signal gets lost, so it's fine. And with active readers, let's say you don't check other active readers, there might be other active readers, and you signal, that's also fine because we have this while here. In this while, the writer checks for active readers, right? So even if you signal them and you wake them up, they're not going to necessarily go and write. They're going to come back and check this while loop, and they're going to go back to sleep. So correctness, from correctness point of view, it's okay. From efficiency, it's not efficient because you're waking up a writer while there might be some active readers. So it's going to get scheduled and go back to sleep. So it's kind of like inefficient what you're doing here. So correctness doesn't change, efficiency gets less efficient if you don't check this. Now let's ask another question. What if instead of signal, I send a broadcast to all the writers? Would that change the correctness? And if not, what about efficiency? Now, if you think about this, the answer is very similar to the previous one. So correctness is not going to change. You're going to wake a whole tribe of writers, but we know that only one of them can go and start reading and writing to the data. So all of them, if they wake up, one by one, will come here and check. And if let's say you have 10 writers and all of them get a signal with the broadcast, all of them wake up, only one of them can go and write, and the other 9 will again check and go to sleep. So again, correctness is fine. You're sacrificing efficiency, right? Efficiency goes down because now you're going to run all the writers. And that was not necessary. What if instead of having 2 condition variables, 1 condition variable for OK to read and 1 condition variable for OK to write, what if I have only 1 condition variable, OK to continue, right? And I just use that one in both of these functions? Would that change the correctness of my code? I'm going to give you some time to think about it. Now, this unfortunately will jeopardize the correctness of our implementation. So here's an example. You might send, let's say that let's go back to the example that we saw. So at some point, W1 came and went to waiting. And then R3 came and also started waiting. So in our previous example, R3 was waiting on OK to write, to read. And W1 was waiting on OK to write. Now, if we have only 1 condition variable, then both of these 2 guys are going to wait on OK to continue. Now, in our previous example, once the active readers were done, they would send a signal to this OK to write and would wake up W1. Now, in this example, when R1 and R2 are done, they're going to send a signal to OK to continue. Now, I have 2 threads waiting on OK to continue, W1 and R3. There is a possibility that the signal is delivered instead of to W1, the signal is delivered to R3. If that happens, then R3 wakes up. And where does it wake up? It will wake up here. So it's going to go up and check the condition again. And there is still a waiting writer because the W1 is still here. So it's going to wait again on this OK to continue. So R3 wakes up, checks the condition still holds, so it puts itself to sleep. Now what happens? Nothing. Now R3 and W1, both of them are going to wait. And if there are no other threads in the system, you have a starvation. Now this will continue forever. Both W1 and R3 are going to wait forever. So this change, going from 2 condition variables to 1 condition variable, could cause a starvation. And so it's not correct. Another question, what if, so the problem here was I had a signal, and this signal could be delivered to a wrong person. What if instead of signal, I put a broadcast everywhere? So I always broadcast. Would this work? So I'm still using a single condition variable, but every time instead of signal, I'm going to just do broadcast. Somebody is asking, W1 should be able to continue since AW and AR are 0. Yes, W1 should be able to continue, but if you use signal, only one thread gets the signal, and who gets the signal is not clear. And the signal could be delivered instead of being delivered to W1, it could be delivered to R3. And in that case, the signal gets wasted and we don't have another signal. So there was only one signal. It was delivered to the wrong person and got wasted. And now we have a starvation. If it was delivered to W1, then it would have been fine. But if mistakenly or by chance it's delivered to W1 to R3, and we don't have any actually say, so when you send a signal, you don't have a say who gets that signal. The operating system, whoever is implementing, decides who gets the signal. Okay. Right. So what about now? I changed it to a single condition variable, but instead of signal, I'm always using broadcast. Now this implementation actually works, but it's extremely inefficient, right? Because in this case, both W1 and R3 will wake up, and then R3 puts itself back to sleep, and then W1 continues. So this works correctness-wise, but it's extremely inefficient because you're waking everybody up on every event, and then they have to check and put themselves back to sleep, which is kind of pointless. Now, another question. In our implementation, we sort of gave some priority to writers. So if you remember, the first thing that we're giving priority to writers is here. We're checking if there are waiting writers, but here we're not checking if there are waiting readers. So, if let's say W1 came and started waiting, then R1 came and started waiting. Sorry, R3. Now, if W2 comes, let's say W1 is done, it sends a signal to this guy, it becomes ready. But right before we run it, W2 comes. Now, W2 does not need to wait for this guy. If it gets scheduled, it actually runs, right? Because here we're not checking waiting readers. Because there is no active writer or active reader, W2 gets priority over R3, even though R3 came to the system first. Now, can this lead to a starvation for readers? So this is one, actually. This is one kind of giving priority to writers. The second one is here. So when we're signaling, we first look at waiting writers to signal them, and then we look at waiting readers. So here again, we're giving priority to writers. So this indeed, yes, can starve the readers. So in this implementation, if you keep having writers, your readers could starve. So forever they could just wait and wait and wait and wait. If you keep having writers, then your readers could starve. So if you want to have a starvation-free lock for your readers, this implementation is not going to do it. So you have to tweak it and change it so that it's starvation-free for your readers. What about writers? Can writers starve? And the answer is yes. This one is a little bit trickier to see how a writer can starve. I'll try to show you. Let's say you have W1, W2, W3, all of them waiting. Or no, let's actually assume that there is writer 1 waiting. So after R1 and R2 are done, they make W1 ready. Now, this doesn't mean that W1 is going to be scheduled. It means that it's going to be ready. Now, let's say before it runs, W2 comes. Now, when W2 comes, it's ready, right? It hasn't yet run, so it becomes ready. Now, operating system looks at the ready queue. It sees W1 and W2. And maybe operating system chooses W2 to run. So W2 runs and it becomes running. If later on W1 runs, it sees that there is an active writer, so it goes back to waiting. Now this cycle could continue. Now let's say W2 is done and sends a signal and makes W1 ready. But right before W1 runs, let's say W3 comes with ready. And let's say operating system again picks W3 and makes W3 running. Then W1 again goes to waiting because it checks and there is an active writer, so it goes waiting. And again, this W3 could signal W1, make W1 ready, but before it runs, W4 comes. So this could continue forever. So W1 never gets a chance to run because basically we're not doing any kind of first come, first serve. We're just leaving it to the operating system scheduler to pick the next writer. So in this case, W1 could actually starve. If you want to solve this problem, you can actually think that you might want to, for acquiring the right, you might want to put this waiting writer here to see if there are other waiting writers, you should wait. Now, this is not going to work. You can convince yourself, I mean, I have it because I'm running out of time. I'm not going to tell you why, but you can read it. So it's not going to work. So another thing that you might want to do is to implement this FIFO, first come, first serve, manually. How can you do it? You can try, this is take two, to say how many writers, you know, it's kind of like a, like when you go to bank and they give you a number, so whoever gets in, they get a number. So we're adding internal state to our lock, and the internal state is the number of writers. So every time a writer comes, we increment number of writers. So we know how many writers we have. We also have next to go. So who is the next to go? So we have these two variables. Now, Again, you can convince yourself that this also doesn't work. So it could cause signals to be wasted and a starvation to happen. So everybody will wait. Again, I'm not going to go into it. You can read it and convince yourself. So this is also not enough. So here comes take 3. So we not only need these, these who's next and the number of riders, we also need to give each rider their own condition variable. So we're going to have each rider, instead of having a single OK to write, we're going to have each rider to have their own condition variable. So here is how we're going to do this. So each rider creates its own condition variable, adds its condition variable to a queue, and this is how we're going to implement the FIFO. So whoever pushes its condition variable to the FIFO is going to be the next one who gets the signal. So this is how we're going to make sure that the signal is not going to be wasted. And we're going to have FIFO of riders. So we have this. So we added these two. We add one condition variable per rider, and we add a queue to implement this FIFO. So we added, initially we had these active riders, active readers, waiting riders, waiting readers. Now I added 4 more variables: number of riders, next to go. Each rider now has its own condition variable, and we have a queue of condition variables. So this is how it's going to work. Now, when you signal, so when you want to release, then you go and look at the condition variable at the top of this queue, and you send this signal to that specific condition variable. So instead of having all the riders wait on the same condition variable, we make them wait on their own condition variable, and then we pick the right condition variable and signal that one. And then you can see that this will work. Okay. So that's that. So hopefully this was like just a session for you guys to look at using condition variables in a more advanced context. In the lectures on Tuesday, we will see how we can implement condition variables in the operating system. So I have a bunch of questions here. So I thought we assumed that we have more writers than readers. Or is it the other way? We're not talking about the number of readers and number of writers, right? So if you're asking about the starvation of readers, if your writers come more frequently, then they can, because they have more priority than readers, they can starve the readers. We're not making any assumption in this implementation about how many readers we have, how many writers we have. We have our implementation, and now we're discussing how this implementation works. Now, if you have a system where writers come very infrequently, then you shouldn't worry about starving the readers, because it probably doesn't happen. If your writers are coming really infrequently, then whenever they come, they get some priority to write their data, and then they go, and then the readers will continue reading. If, however, you have a system where you have the same amount of readers and the same amount of writers, or the frequency of writers coming is high, then you probably want to modify this implementation, because this implementation will starve your readers, right? So that's pretty much what we did with the analysis. We were just looking at a specific analysis and talking about it and analyzing it and saying with what systems this is a good implementation and with what it's not a good implementation. Another question, for take 3, you would have to advance how many riders there are. Oh, you need to know in advance how many riders there are. No, you don't. No, you don't, because so each one of them, every time they come, they create their own condition variable, and then they add their condition variable to this queue. You know, as long as this queue is dynamically resized, you should be fine. So you can push as many condition variables as you want. And then you always are looking at the head of this queue, right? So that's fine. So you don't need to know in advance how many writers you want. Oh, so because of the queue, no, this might be any data structure that could be resized dynamically, right? So you're just, you know, let's say it's a vector and you're just appending to the end of the vector, right? So that's pretty much what I mean. It's not a bounded queue. It's not a queue with a maximum length. So okay, so it is the frequency that matters. Yes. So if you get a lot of writers, they're gonna just, you know, starve the readers. Oh, okay, got it. Okay, glad. Thank you for sticking around, and thank you for attending the tutorial. I hope it was helpful. Again, this is not you know, a programming course. It's an operating system course. So the purpose is to look at the implementation of CVs, but I thought that you probably didn't see condition variables much in action as much as you saw semaphores. So hopefully this example gives you that, you know, more advanced look at condition variables. So that's that for today. Thank you for those of you who are also watching this after the stream, online streaming. Take care, be safe. Talk to you later. Bye-bye.